Alright, so welcome to 3030, and today we are going to discuss section 16. So this is the last topic of the 3030, that is the memory system and memory technologies. And here we are going to have an overview of the memory system today, and then in the following lectures we are going to have detailed discussions on each memory technologies one by one. So today is like an overview of the memory system. And this is a reference chapter in the supplementary reading list. And this is chapter 15.2. So let's get started. And the memory system is a very important component in the von Neumann machine. So this is a generic architecture for the von Neumann machine. You have seen this before, I guess. So you have the processor, for example, the central processing unit, CPU, and then this CPU does the computation for you. For example, it may have the logic to do the addition, summation, multiplication, and so on. And then you need the data to do those processing. So those data will be stored in the memory component of the system. So here we have the generic box representing the memory, and you are going to store the data in the memory. So the processor needs to give an address to the memory component to fetch the data. And then you are going to fetch the data back to the processor to do those computation. And after the computation is done, for example, if you are doing two-vector multiplication, and your dot product from that multiplication needs to be sent back to the memory for the storage. So we have this kind of loop in the computation. So you are doing computation in the processor, and after the computation is done, you save the data to the memory. And next cycle, you fetch the data back from the memory to the processing unit. So this is the concept of the von Neumann architecture. And if you take a closer look at this kind of computer system, so this is a generic organization. So we have those processor units, and then the memory components, and then we may have the I/O devices, like the input and output for the interface to the users, like your keyboard or your display. So this data will be transferred between those components through the data bus. And this is a generic organization for a computer system today. And then we are going to discuss in more details about the memory components in the system today. Here, if we look at the memory system, we will find out there will be a so-called memory hierarchy. So here we are going to take a close look at this memory hierarchy. So in the memory system, there are different levels in the system, and we call it hierarchy. And here we have the processor, for example, in this blue box. And in this processor chip, we will have the logic components, which I didn't show here. For example, you may have your adders, multipliers, and your finite state machine controls, and so on. So we didn't show that in the processor box here, but we only highlight the memory component in the processor. So those memories are within the same processor as the CPU. So we call it on-chip memories. So here, those red boxes, the first one is register. So this is to store the most intermediate data to your processor. For example, if the processor next cycle will take two vectors to do the multiplication, so those two vectors will be stored in this local register. And the register typically has very small capacity. For example, you can only store 256 bytes in the register, but you can access it very quickly. So if your clock cycle is 2 gigahertz, then you can access your data within 0.5 nanoseconds. So basically 1 clock cycle, you can get the data in. So I see there's one question somewhere. So I will go to that point later why the DRAM is outside. So what is within this blue rectangle? This is your processor chip. It's your CPU chip. So some of the memories are embedded into the CPU chip. This is on the same chip. And we'll talk about DRAM later. So on the same chip of your processor, the closest to your processor will be the register. And then after the register, we'll have different levels of the cache. And we will later see that those caches are made of the SRAM technology. This is a static random access memory. And we have the whole lecture 17 to talk about the SRAM. So I will give the details later. But today, we are going to look at the overall organization. So for the caches, there are different levels, like level 1, level 2, level 3. So you see the differences here is in the capacity and the access latency. So the L1 cache, relatively smaller. For example, here 32 kilobytes. L2 larger, like 128 kilobytes, and L3 8 megabytes in this example. As you increase the capacity, the speed will become slower, or the access latency will become larger. For example, L1 cache 1 nanosecond, L2 cache 2 nanosecond, L3 cache 5 nanosecond. So you see the trade-off between the capacity and the latency. So those are the caches. And then these caches are still on the same chip with the processor. So those are on-chip memory. And then we talk about the DRAM, which is off-chip. Off-chip means what? Means there's a separate chip. It's another chip. Okay. So latency. What is latency? Latency is a delay. You can think latency is the same as delay. So latency technically means delay. And the DRAM is a separate chip. And you can have even larger capacity, like 16 gigabytes. And you need about 40 nanoseconds to access the data from the DRAM. So this DRAM is the run in the spec of your electronic products today. You have seen that specs for example, your smartphone. Your RAM is like 4 gigabytes, 8 gigabytes. That is this DRAM, dynamic random access memory. We will talk about that in more details in the lecture 18. And then if you go to further right, we have those data storage units, like the flash memory. So this is the technology for the SSD, solid state drive. And also you may have the magnetic hard disk drive. So this is for even larger data volume kind of storage. For the hard drive, these days you can have tens of terabytes data. But you need a very long time to access the data. So this is latency, like milliseconds. This is slow. And SSD is relatively faster, but the capacity is typically like hundreds of gigabytes these days. You need like around 50 microseconds to access the data. So you can feel the difference, right, in your daily life. If you have a computer, desktop with the hard disk drive, when you boot up the system, it will need longer time. And the solid state drive SSD will enable faster boot up of your system. So you can feel the difference in terms of the speed. And here there's another differences between the technology. One is volatile memory. The other one is non-volatile memory. So here, the register caches and DRAM are all volatile memory. And here, the magnetic hard disk drive or the solid state drive based on flash is non-volatile memory. So what does this volatile mean? So here, this is a key conclusion. Volatile means after power off, if your data is gone, then this is the volatile memory. So your data is gone after power off. Non-volatile memory means your data is still there, data kept after power off. So you can see the differences between the volatile versus non-volatile memory. After you remove your power supply VDD, then you can still keep your data in your SSD or the hard disk drive or the non-TAN data storage. But all your data stored in the cache or in the DRAM will be gone. So any questions in this slide? If you have a question, you can use the chat function here, or you can unmute and ask the question. All good? So we can take a closer look at this memory hierarchy. And again, this shows the different levels or different technologies in the memory system. And again, this box stands for the chip for the processor. And on the processor, you may have multiple cores these days. It's multi-core processor. And within each core, of course, you will have a lot of logic components, like your adders, multipliers, and so on. But you will also have some local memory components, like those register and here are like L1 cache. And then you will have also L2 cache, L3 cache on the processor as well. But the L2 or L3 cache may be shared between multiple cores. And L1 or L2 cache may be local to the individual cores. And then after the after the processor chip, then you may have separate chips for the DRAM. And this is what you have seen in the motherboard. If you open your desktop and see the motherboard, you will see this kind of DRAM board inserted to your motherboard. So this is a separate DRAM chips. And then this is like the flash. And here you have the hard disk drive. And the hard disk drive is very slow because it's based on mechanical rotation of the drive. So there are many little magnets on the hard disk drive. And then here there's a reader to read the data from those little magnets. And you need to rotate this drive and then use this header to locate individual bits on this drive. So it's very slow because you need to mechanically rotate this, and that's why it's very slow for the hard disk drive. We're not going to discuss more details about the hard drive. We are more interested in the more advanced modern technologies like the flash and DRAM and the SRAM in this course. So again, here we have those trade-offs in terms of the speed, or in other words, this latency. This is how fast you can access the data. It's a delay of time. And then you can translate that into the CPU clock cycle. So if your speed is like a few let's say 0.3 nanoseconds, if you translate the clock frequency, will be like 3 gigahertz. You just need 1 clock cycle to read out the data from the register. And then the register only has like hundreds bytes capacity. And L1 cache will be larger than the register, but slower. And then you can have the different L2, L3 cache. So you will have larger and larger capacity, but slower and slower speed. Where is the L1 cache in the picture? It's in the right of the internet like the other cache. So here, I think it's this orange and purple ones are the L1 cache. So there are two components. One is instruction cache, one is data cache. Instruction cache means it's going to store the instructions from your computer system, like the instruction to read, write, this kind of commands or code. Data, of course, is your data, like your image data. So here we have those trade-off between the speed and capacity. And that's why we have to use this memory hierarchy in the system. Of course, ideally, you want larger capacity and smaller latency or faster speed, but you cannot simultaneously achieve those two. So that's why we have to use those different technologies in the memory hierarchy. So what do we have this kind of memory hierarchy? We can also use let's say, an example to talk about this. For example, if you are taking a picture using your smartphone, right? After you capture the image, then if you want to edit your image using your apps, so you need to load in your image into the cache, for example, and then your program will, let's say, do something on your pixels of the image. So you need to load in those pixels from the cache to the register, and then you will do the modification. Your software program will do the modification of those pixels. And after you are done with that, you need to save that back. And then if after this image is processed, then you need to save it back to the flash. You save it, and then you can store it for a long time. So you need this kind of hierarchy in the memory system because those registers not large enough to hold a high resolution image, because that will be very large if you are doing high definition images. You cannot hold all the image in the register. You have to save part of the data in the different level of caches, and then the closest to your processor will be the next, let's say, next data you want to process. You have to do it sequentially. So you need to prepare the data ready in the register, but you cannot prepare all of them at one time. So you have to store some of them in the cache, and then you can load it to the register sequentially, and then you do the computation. And after you are done with all the computation, then you need to save the data back to the DRAM and eventually to the flash for the long-time data storage. After you power off the chip, you still want your data there, your image there, so you need to save it to the flash, the SSD. So any questions? All right, so here is just another graph showing this kind of trade-off between the area and the access time. This access time is what we discussed, like the latency. So area is the area to store 1 bit of data. So later we will say that SRAM is made of 6 transistors. So you need 6 transistors to store 1 bit of data. So it occupies some space. So this is the area. Relatively, this area is large. But SRAM is fast, so the latency is small. And later we will say that DRAM is 1 transistor, 1 capacitor. So if you draw the circuit diagram, it will be something like this. 1 transistor, 1 capacitor. And then of course you can see that this is smaller than the SRAM. SRAM you have 6 transistors. So here the area will be smaller, but the speed will be slower for this one. And later you will see that the flash is a single transistor and it's single floating gate transistor. So it's even smaller than the DRAM, but the flash is even slower. You need longer time to access the flash data. And then we have the magnetic drive. So this can be very high density, but it's pretty slow because we have to rotate this one, mechanically locate those bits on this drive. So you see this kind of trade-off between the area per cell, let's say area per cell, or let's say area per bit. If you want to store 1 bit of data, you need some area. And you see this kind of trade-off. So ideally, you want something here. This is your ideal target. If you can have a magic technology that can offer you small area per bit and also small latency, that means fast operation, that will be the best. But unfortunately, there is no such magic technology of today. So we have to have this kind of trade-off with different technologies to serve different levels in the memory hierarchy. So any questions here? So this table also summarizes the trade-off between different technologies. I will not repeat that. So basically, it's a trade-off between this density or the speed. So the density is 1 over area. If the area is small, then you can save a lot of bits at a unit area. So that means the density is high. So here, this is a trade-off between technologies. I will stop for this clip.